We're going to continue our lesson on verifying trig identities. Remember, and I've said this many times, you are not solving an equation because we have not yet proven that this is true. Our job is to prove that it's true. So when you start on this, you'll start by working on the more complicated side of the equation. Well, unfortunately, they both look equally complicated. So on a situation like this, my recommendation is that you work on this side because the denominator is a single value. And what you would do is multiply numerator and denominator by this. So when we do that, I'll just put it in parentheses. I get secant of s minus tangent of s over secant of s minus tangent of s. I apologize that this isn't the nicest looking thing, but if I'm multiplying these two, right, I'll distribute secant times secant, that's secant squared. Secant times tangent minus secant times tangent, that'll cancel out and become 0. Negative tangent times positive tangent is negative tangent squared. And for now, I'm going to leave the denominator exactly as it is. Here's that vertical line. If I use my Pythagorean identity, I see that secant squared of s minus tangent squared of s is equal to 1. That means that we would have to rearrange one of our identities, but that is in fact the case. So what we're left with is 1 over sine of s times secant of s minus tangent of s. Then I can actually separate this out as 1 over the sine of s times 1 over secant of s minus tangent of s. Well, I know that 1 over the sine of s is cosecant of s, and cosecant of s times 1 is simply cosecant of s. And that's what was on the right-hand side. These are equal, so this is an identity. This problem is the first where we're actually going to have to look at both sides. So I will start with the left-hand side, not for any reason because they're equally complicated, but I think fractions are a little bit more daunting than products. So tangent squared of s over secant squared of s. I know some things. I can put tangent squared of s as sine of s, sine squared of s, over cosine squared of s, over 1 over cosine squared of s. And then I can copy dot flop. These cosine squared of s's cancel, and I'm left with sine squared of s. Now I have to start working on the right-hand side and seeing how I can simplify that. The first thing that I'll do is FOIL this out. 1 times 1 is 1. 1 times negative cosine plus 1 times positive cosine, those cancel. positive cosine times a negative cosine would be minus cosine squared of s. Now I can look at my Pythagorean identity, and if I rearrange the first one, I learn that 1 minus the cosine squared of s is sine squared of s. So this checks out, and this is an identity. This last one is a lot more complicated and not something that's going to be easy to see. So again, I will call your attention to the left-hand side as being slightly more complicated than the right. And what I can have you do is you can multiply the entire left-hand side by the sine of theta over the sine of theta. Why did I choose sine? Well, sine squared is in my denominator over here, and truthfully, we can multiply the numerator and denominator of any fraction by the same value. So instead of choosing sine squared, I just chose sine. From there, I end up with sine of theta cotangent of theta minus sine of theta cosecant of theta over sine of theta cotangent of theta plus sine of theta cosecant of theta. So all I did was multiply sine times cotangent, sine times cosecant. That's how I got this. And then in the denominator, sine times cotangent plus sine times cosecant, and I got this. Now I'll start simplifying, and here is that line that I can't cross. So sine times cotangent, that's cosine over sine. And cosecant is 1 over sine.
There is a student.
I apologize for that announcement. So with this, I can cancel out these signs, and here, and here, and here. And I am left with cosine of theta minus 1 over cosine of theta plus 1. This is as simplified as this gets, so now I start working on the other side of the equal sign. What you might notice here is that this looks like a trinomial. So if I let a be equal to the cosine of theta, it's like having 1 minus 2a plus a squared, and that factors to be 1 minus a squared. So when I replace a with cosine, I get 1 minus the cosine of theta times 1 minus the cosine of theta. The denominator is sine squared. It's actually negative 1 times sine squared, and I can go to my Pythagorean identities and say, well, I know that sine squared is really 1 minus the cosine squared. So I'll make this negative 1 times 1 minus the cosine squared of theta. Now I have to remember a lot of my factoring rules. My numerator will stay the same. But I look at my denominator, and that's a difference of 2 perfect squares. And so when I factor a difference of 2 perfect squares, I get 1 plus the cosine of theta times 1 minus the cosine of theta. Now I can cancel. Please notice that everything going on here is multiplying. This is multiplied by this. Negative 1 times this times this. So I can start canceling. This cancels, and I'm left with 1 minus cosine of theta in the numerator. And then my denominator, I still have negative 1, but I'm going to rearrange this denominator because I'm allowed to. 1 plus cosine of theta is the same as cosine of theta plus 1. Then what I'm going to do is I'm going to pull out this negative 1, and I'm going to move it to the numerator. And when I distribute this, this becomes negative 1 plus cosine of theta, or cosine of theta minus 1 over cosine of theta plus 1. And it's a little hard to see because this one goes here, but these do check out.